Hi class, today we're going to talk about compound events. Compound events are bringing more than one event together and calculating its probability. We're going to talk both about independent events, events that don't affect one another, and dependent events, events that do affect one another. Let's start with this example. We have in Colorado, it snows on average 5 out of 7 days every week in the winter. Find the probability that it snows on one day. So real straightforward. That's just 5 out of 7. It snows 3 days in a row. So this is where something in probability always like kind of stuck in my brain. And probabilities, you multiply. Or probabilities you add. So that's something that I just really helped me to do well with probability. And you multiply or you add. So the probability it snows 3 days in a row. So for each of those 3 days, I'm going to put a line. So you want to know the probability it snows one day and another day and another day. So it's 5 7 times 5 sevenths times 5 sevenths. And so multiplying the numerators, you get 125. Denominators, you get 343. And so the more of these days you have to string together, the less likely it'll be. You know, you're like, oh, you're going to get a day off sooner or later, so the less likely it'll be. So naturally, the likelihood will go down. This is approximately 36% likely, whereas, 5 out of 7, that probability is, 71%, almost 71.4%. So the likelihood does go down, but still pretty likely that it'll snow 3 days in a row. Colorado, especially near the mountains, gets a lot of snow. Here we have a probability compound problem that has to do with archery. So we have Marcy that has a 40% chance of hitting a bullseye in archery. Lucy has a 70% chance. And we want to calculate the probability that these following things will happen. I personally like using what is called a tree diagram to calculate these. So I'm going to show you how that works. You start with a left-right scenario. And the left-right scenario is that one person hits or misses. So what you imagine is one person going first. Since we're first imagining or mentioning Marcy, we're going to imagine Marcy going first with a dartboard, and Marcy will hit or she will miss. And so since she has a 40% chance of hitting, we're going to write 0.4, 60% chance of missing, because those two events are complementary, we're going to write 0.6 there. It's always good to write those in decimal form. Now, imagine Lucy goes up to the dartboard. After Marcy, if she hits, either way, Lucy will go up. If she misses, either way, Lucy will go up. That's why we put little branches going off, hit or miss, either way. So because Lucy's better, she has a 70% chance of hitting, 30% chance of missing. And again, I'm writing these in decimal form. And this is the Lucy going to the dartboard. So again, it's compound probability because I have two different events, Marcy going to the dartboard, Lucy going to the dartboard, and it's called a tree diagram because each of these are called branches. So first question is calculate the probability that they both hit the bullseye. So I'm going to highlight that scenario. Hit, hit. And if you go down the tree diagram, you multiply. So down is multiply. So I'm going to multiply. So the probability they both hit the bullseye is the product of that, 0.28 or 28%. And that particular branch represents hit, hit. Marcy hits the bullseye, Lucy hits the bullseye. Now let's do the probability they both miss. They both miss is a different part of the tree diagram. It's over here. Miss, miss. Miss, miss. Again, going down the bullseye. You multiply. That's going to be an 18% chance that they both miss. Going right down that bullseye. Next, Marcy misses and Lucy hits. Marcy misses and Lucy hits. Marcy misses, Lucy hits. That one seems the most likely. Again, going down the tree, you multiply. So that's 42% or 0.42. Marcy misses, Lucy hits it. Now we get to the last one. This is a greater degree of difficulty. This one says at least one of them hits it. So I'm going to clear out all the highlight. Okay, so I'm going to go ahead and highlight. I feel like I'm out of good color, so I'm going to go back to yellow. At least one of them hitting it. So it'll be hit, 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 miss, miss, hit. Those are all of the scenarios of at least one of them hitting it. Either they both hit it, one of them hit it, or one of them hit it. So it's hit, 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 miss, or miss, hit. So hit, hit is 0.28. That's that 0.4 times 0.7. That's hit, hit. That's both hit. Or, remember, or is add. So going down, you multiply. Oh, I should write this. I'm sorry, I'm being lazy here. That's our hit, hit. Or. Then I'm going down this branch right here. I could do hit, miss. Hit, miss. That's 0.4 times 0.3. That's 0.212. That is hit, miss. So you could do hit, hit, or hit, miss. Or means add. So plus. Or you could miss it and then hit it. So that's 0.6, 0.7, which is 0.42. So again, you can do hit, hit. So that's Marcy hit, Lucy hit. Or Marcy hit, Lucy miss. That's hit, miss. Or miss, hit. Marcy miss, Lucy hit. So or. Whenever you say or, you add. And going down the branches, you multiply. So if we added all those up, so it's 0.28 plus 0.12 plus 0.42, that is 0.82. So 82% chance that at least one of them hits it. And again, it's or, because you can't do all of these or two of these, it's or. But there's a really fast way to do this that doesn't involve all this math. You could do the complement. The complement would be 1 minus the opposite of this. So the opposite of this is 1 minus the opposite. So 1 minus at least one of them hitting it. So what's the opposite of at least one of them hitting it? It's 1 minus both missing it. One minus both missing it is 1 minus 0.18, which is 0.82. That's using the complement, which we talked about yesterday. So that's another way to do it. So that's a tree diagram. I love the trees. Just makes everything a lot clearer. Also, it is super helpful with dependent probabilities. Now, this is independent probability. What I mean by that is how Marcy does, doesn't at all affect how Lucy does. So if Marcy gets the bullseye or doesn't, it didn't affect Lucy's performance at all. But it could. Lucy could want to do better if Marcy misses, or it could throw her off. She could do worse. Dependent events are where if one thing happens, it affects the outcome of the other. Happens all the time in sports, but also it happens with probability, like a lottery, or in this case, a very simple lottery. A box contains, and this says, dependent events are events for which the occurrence of one of the events does affect the occurrence of the other event. So a box contains 2 red and 2 yellow tickets. 2 tickets are randomly selected, the box one by one without replacement. That's why it's dependent. If you take one ticket out and you don't replace it, the probability is then affected in the future. Find the probability that both are red. So if we do a tree diagram for this, we have the draw of the first ticket. I'm going to do a little, oh my gosh. Okay. Yeah, I'm going to do a tree. So let me move this puppy over a little bit. So we're going to do, this is the first draw. So if you do the first draw, you could pull a red or you could pull a yellow. The probability of a red, I feel like my brain hurts that the yellow is in red. Okay, I have to fix that. Red, yellow. Ooh, sorry. Red, yellow, and then we have the first draw. So you're going to draw the first ticket. That's what I mean. You're going to draw the first ticket. Probability of a red, well, we have 4 out of 6. 4 out of 6 tickets. So the probability of a red is 4/6, which is 2/3. 4/6 reduced is 2/3. Okay. Probability of a yellow is 2/6, which is 1/3. You know what? I'm not going to reduce these. I feel like it's going to be confusing. Okay, probability of a red is 4 out of 6. 4 out of 6 are red. Probability of a yellow is 2/6. And that's for the first draw. Now the second draw, let's go from there. We're going to draw the second ticket. Now, if the first ticket was red, think of it this way. If the first ticket is red, there is now one red ticket gone, okay? So this is where we're in our dependent probability. So there are 3 red tickets left out of 5. This is where it gets real thoughtful, okay, students? So if you draw a red on the first one, there's only 3 red tickets left out of 5. Okay, this is going to require some thinking here. If you draw a red on your first, how many yellows are left? Just 2. There's still 2 yellows left out of 5. Okay. Now, if on your first draw you drew a yellow, what's the probability you'll draw a red? Well, there's still 3 red left out of 5. There's only 5 tickets left because you've drawn 1 out. Well, how many yellows are left? Well, if on your first draw you had a yellow, 1 yellow is gone. So there's, oh man, I messed up. I'm sorry. Oh, I have to go back. There's 4 out of 5 reds. My bad. So here, let's go back. For this, you drew a yellow. Okay, so we drew 1 yellow here. So what's the probability that you drew a red? Well, there's still 4 reds left out of 5. Still 4 reds left. Okay, now let's look at the yellows. How many yellows are left if you drew a first yellow? There is 1 yellow out of 5. Okay, so this one's a little tricky. So for your initial draw, the probability of red is 4 out of 5. The probability of red is 4 out of 6. Probability of yellow is 2 out of 6. Then if you drew a red, there's only 3 reds left out of 5 tickets, but there's still 2 yellows left out of 5. Now going over here, if the first ticket you drew was yellow, you still have 4 reds left, but there's only 1 yellow left. So that's the way it's called a dependent event, because number 1, there's less tickets left. There were 6 tickets, now there's 5 tickets left, so the denominator changed. Also, if you've drawn 1 red, there's 1 less red. If you've drawn 1 yellow, there's 1 less yellow. One thing to note, these add up to 1. These have to add up to 1. And these have to add up to 1. If they don't, then something's messed up with your probability. So A, from the probability that they're both red, what you would do is multiply down the red. So that would be down this branch, red times red is 4 6 times 3/5. That is 12/30, which reduces, I have to divide it by, let's see what goes into both of those, 6, so 2/5. The first is red, the second is yellow. So for B, first is red, second is yellow. We can go down that. First is red, second is yellow. 4 6 times 2/5. We get 8/30, which is 4/15. Tricky. So hopefully, as I talk through that made a little more sense. Dependent events, they are tricky. All right. So here we have a hat containing tickets with the numbers 1 through 20 printed on them. If 3 tickets are drawn from the hat without replacement, that means dependent events, Determine the probability that they're all prime numbers. So let's think of what the prime numbers are. Let's say 2, 3, 5, 7, 11, 13, 17, and 19. So we want a prime and a prime and a prime. So because it's and, I'm using multiply. So the first one is out of 20. Out of 20, how many primes do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 20. We have 8 out of 20 primes. So this is the first draw. Now for the second draw, if the first draw, we got a prime. For the second draw, how many primes are left? 7 out of how many tickets? 19. Yeah. You have 7 primes left out of 19 tickets. And then you have 6 primes left out of 18 tickets for your third draw. So every time the number of prime numbers goes down because you took one away, another away, and then you have 20 tickets, then 19 tickets, then 18 tickets. Every time it goes down by 1. So in the end, you're going to have 336 over 6,840. And that, I use my calculator to reduce that, 14 out of 285. Crazy, crazy. That's the reduced fraction. Okay, so in class, until the end of class, you will work on this. And I will see you at graduation.